So dear students, we want to continue with our application of Gauss's law. So in this video we are going to study the second application of the Gauss law, and that is to find the electric field due to an infinite plane sheet. So our intention here is to find the value of the electric field due to an infinite plane sheet. So I'm drawing the plane sheet here. So this is my, let us take, infinitely long plane sheet. Infinitely long plane sheet, and let us take, it is uniformly charged. Uniformly charged infinite plane sheet. So electric field due to uniformly charged infinite plane sheet. So here it is uniformly charged, and our wish here is to calculate what will be the value of the electric field at its periphery due to this particular infinite plane sheet. So for that I want to draw a Gaussian surface this way. Okay, so let this be my Gaussian surface. So it is a cuboidal Gaussian surface which enclosed this particular plane sheet inside it, positively charged plane sheet. This portion of the plane sheet, it cannot occupy, or it cannot enclose the infinite plane sheet, but it encloses this amount of plane sheet inside it, and this particular surface here is your Gaussian surface, which is cuboidal in this case. In this case it is a cuboidal Gaussian surface. In the previous case of infinitely long uniformly charged infinite wire, we have considered a cylindrical Gaussian surface, but for this infinitely long plane sheet we have considered cuboidal Gaussian surface. Now let's see in which directions do this plane sheet contribute the electric field. So basically there are three possible directions for this cuboid. One is, this is your x direction, let us take, and let us say this one is your y direction, and this upward direction is your z direction or z direction. So x direction, y direction, z direction. So first of all, see towards this y direction. If you see towards this y direction, this y direction will be the direction along the plane sheet. This y direction is the direction which moves parallel to the plane sheet itself. This direction moves along the plane of this plane sheet. And if we consider electric field along this direction, then this particular if Ey will be the electric field along y direction, then what will happen is this particular electric field along y direction will force this charge to move along the surface of the plane sheet, because electric field is along the surface of this plane sheet Ey. So this will force the charged particle to move along the surface of the plane sheet, and we already have an idea that we are dealing with electrostatic in our discussions. That means in this discussion charges should not flow. Charges should not flow. So if there were electric field present along this y direction, then the charges will light. Then electric field will move along y direction, or the charge will move along the surface of this plane sheet. Then it will contradict our assumption of electrostatic. Hence, the electric field along the y direction will not be present in this case. It will be zero. Similarly, if we consider electric field along z direction is also parallel to the surface of the plane sheet. And if we consider the electric field along z direction, then it will force the charged particle to move along the surface of this plane sheet, because z direction and plane surface of the plane sheets are parallel. So the electric field along the z direction will force this charged particle to move along the surface of the plane sheet, and which will again contradict our assumption of electrostatics, which means charges shouldn't flow. Hence, in this case also the electric field along the z direction will be zero. If it is not zero, then charges will start to flow, which contradict our assumption of electrostatics. So now the only direction, okay. So if Ey is zero in this direction, then electric field Ey will also be zero in this direction, because this is also parallel to the surface. If Ez is zero in this direction, then Ez downward will also be zero, which will be also parallel to the surface of this plane sheet. Now the only two directions possible are x-axis towards this direction and x-axis towards this direction, two opposite x-axis. And if you see closely, Ex, the direction of the Ex is not parallel to the surface in this case. The direction of electric field along x direction will be perpendicular to the surface of this particular charge sheet, and which do not force the charged particle to move out of this sheet, because there is no medium outside, such that this electric field along x direction will not force any charged particle to come out of this particular charge sheet, because there is no medium to come out. Hence, there will be electric field along x direction as well as the electric field along this direction. Let the value of the electric field along x direction and this direction is E. That means electric field along this direction is, let us take E, and electric field along this direction is E. Now the only surface perpendicular to the, or only surface which is whose area vector is parallel to the electric field is this surface only. This surface is the only surface which is perpendicular to the electric field, or the area vector of this particular surface is parallel to the electric field, because the area vector of this surface is along this direction, and even area vector of this surface is along this direction, which is parallel to the electric field. Hence total flux through the Gaussian surface, through the Gaussian surface will be equals to this E dot A plus this E dot A, this E dot A plus this E dot A, and there will be no contribution of the other surface. For example, there will be no contribution of this surface, because E along this direction is 0, so E dot A is also 0. E dot A will be 0 in this direction because E is 0. Even in this direction, Ez is 0, that means E dot A is 0 in this direction. And towards this backward area, Ey is 0 in this direction, that means E dot A is even 0 in that direction. And for this frontal face, Ey is 0 along this direction, that means E dot A will be 0 in this direction. So the only E dot A exists is for this surface and for this surface, for which E exists, electric field exists. And if you can see, and as you can see, the direction of E and E is same. That means Ea cos theta plus Ea cos theta, and theta is 0 for both the cases because E and A have the same directions. That means cos 0 will be 1. So Ea cos 0 plus Ea cos of 0. So cos 0 is 1, so this is Ea plus Ea is equals to 2Ea. So if this is the area of this surface, and if this is the area of this A is the area of this surface and A is the area of this surface, then total electric flux flowing out of these two surfaces will be equals to 2Ea. Now according to Gauss's law, total electric flux phi, total electric flux flowing out of any closed surface will be equals to phi will be equals to charge enclosed by the surface divided by permittivity of the free space. So this is our Gauss's law. So through the flux we have calculated phi to be equals to 2Ea, and from Gauss's law this phi is equals to Q by epsilon naught. If this is equation 1 and if this is equation 2, so comparing 1 and 2, we'll get 2Ea is equals to Q divided by epsilon 0. But we don't know what is the charge enclosed. What we don't know here is what is the charge enclosed by this Gaussian surface. So we only know a charge plane sheet is enclosed by this Gaussian surface, but what is the value of the charge contained in this plane sheet, we don't know. Or what is the value of the charge enclosed by this Gaussian surface, that we don't know. What we know here is, we know the surface charge density of this the sheet. Surface charge density of the sheet will be equals to sigma. Sigma is nothing but it is the surface charge density, which means charge per unit area. Surface charge density means charge per unit area. So charge per unit area for the plane sheet is sigma. Let us take this is your sigma, a Greek letter. So sigma is the charge density of the sheet or charge per unit area of the sheet. And we know the area of the sheet is also equals to A, because it is enclosed by the Gaussian surface whose two of the sides are A. So if these sides are A, then this size of the sheets enclosed, or the area of the sheet enclosed will also be equals to A. So if sigma is the charge density of the sheet and A is the area of the sheet enclosed by the Gaussian surface, then our total charge enclosed will be Q is equals to sigma into A, because sigma is the charge density, and if A is the area of the sheet, then the charge will be equals to charge density into area. So Q is nothing but Q is equals to sigma into A divided by epsilon 0. Here A and A will get cancels, so E will be equals to sigma by 2 epsilon 0. That means this is the value of the electric field due to this infinite plane sheet, which will be equals to sigma by 2 epsilon 0, where sigma is the charge density of the sheet, or it is the charge per unit area of the sheet, and epsilon 0 is the permittivity of the free space. Now if you see closely here, there is no dependence of distances. This sigma is also a constant and this epsilon 0 is also a constant. That means electric field due to an infinite plane sheet will be constant irrespective of any distances. That means if you consider the value of the electric field at this point nearby this infinitely plane sheet, at this point also the value of the electric field will be equals to sigma by 2 epsilon 0. At this distance is also equals to sigma by 2 epsilon 0. At this distance also the value of the electric field will be equals to sigma by 2 epsilon 0, because there is no dependence of any distance. So at any distances perpendicular to the sheet, the value of the electric field remain constant, and the direction of the electric field will be equals to, if this is the direction normal to the sheet, this is this plane sheet and this is the normal direction to the plane sheet, then the electric field will be normal to the plane sheet and it won't depend on the distance. The value of the electric field will be constant everywhere along this normal direction, here also, here also, here, and every point normal to the plane sheet, the value of the electric field do not depend upon distance, it always remains constant. Hence the electric field due to an infinite plane sheet will be equals to E is equals to sigma divided by 2 epsilon 0 and cap. So this is the electric field due to infinite plane sheet, sigma by 2 epsilon 0. So this is it for today.